Okay, this video is from Chapter 4, Section 4, and the topic is graphs of sine and cosine, and these are called the sinusoid functions. What we'll learn about the basic wave patterns of sine and cosine. We'll learn about sinusoids and transformations, and modeling periodic behavior with sinusoids, and why sine and cosine gain added significance when used to model waves and periodic behavior. So here we have two graphs, and one is the sine function, y equals sine theta, and on the bottom we have the cosine function, x equals cosine theta. And if you recall, the reason we have the distinction here, we know that cosine of an angle on the unit circle is the x coordinate of a point on the unit circle with the terminal side of the angle, and the y coordinate of that point is the sine of the angle. And so if you take a look at the two graphs and just compare them, here's the origin and the origin, you'll notice that the sine function, these are the parent functions now. The sine function starts at the origin, and the wave goes up to 1, back down to 0, down to -1, up to 2 pi, and continues on. Now, what we're going to focus on for now is from 0 to 2 pi, what happens? Well, we say that this sine wave completes one full cycle. Okay, we start at 0, we go up, down back through 0, down to -1, and back up to 2 pi. That's one full cycle of the sine wave. And these values, intermittent values here, this is pi over 2, this is 3 pi over 2. So the sine function attains a value of 0 at 0, it attains a value of 1 at pi over 2, it attains a value of 0 at pi, it attains a value of -1 at 3 pi over 2, and it attains a value of 0 at 2 pi. And the cosine function is very similar, and if you look at the pattern in the waves, you'll notice that the cosine function is just the sine function shifted over. So the cosine function actually starts at 1 when theta is 0, and it goes down, bottoms out at -1 when theta is pi, back up through 0, back up to -1 when theta is 2 pi. So this point here, we complete one full cycle of the cosine wave. So one cycle of the cosine wave looks a little different than one cycle of the sine wave. But overall, the wave pattern of the two functions is very similar. So we define a sinusoid to be a function that can be written in the form f of x equals a times sine of the quantity bx plus c, all that plus d, where a, b, c, and d are constants, and neither a nor b is 0. And you could take out the sine here and put cosine in, and that would be a sinusoid as well. One of the properties of a sinusoid that we can talk about is what's called the amplitude. And the amplitude of a sinusoid function is the absolute value of a. Now, graphically, the amplitude is half the height of the wave. So here's what that looks like. This green line that I have here, this is the height of a wave measured from the theta axis, or what we normally think of as the x-axis. So if I were to draw a line from the height of this wave down to the x-axis, whatever that length is, that's called the amplitude. So we can talk about the amplitude here. Now on the graph, the distance from here to here we would say is -1, but the absolute value of that is 1. So this function here has an amplitude of 1. Absolute value of 1 would equal 1. And so when we have a coefficient on sine that's something other than 1, this wave can stretch vertically or could compress vertically depending on the value of a. We talk about the period of a sinusoid function. So the period of a sinusoid is 2 pi over the absolute value of b. So b is going to be the coefficient on x inside the parentheses here. And it doesn't matter if we're talking about the sine function or the cosine function. This is how we calculate the period of one of these sinusoids. So we have a little formula here, 2 pi over the absolute value of b. Graphically, the period is the length of one full cycle of the wave. So how long does it take for the function to complete one full cycle of a wave? Whatever that length is, that interval, the length of that interval is called the period. So here I have an illustration. I'm using the cosine function. So the cosine function, if we start at theta equals 0, the cosine function starts here and it travels down through the axis, down to -1, back up. And when it gets back up to 1, we say that that has completed one full cycle. So that length from here to here, okay, this distance, that's the period of the function. So the period of the cosine function is 2 pi. And again, if you look at the function itself, y equals cosine theta, theta is our variable. What's the coefficient here? That's a 1. So 2 pi over the absolute value of 1 is 2 pi. So that's the period. So we can talk about a horizontal stretch or shrink and period. So the relationship between what we call a horizontal stretch and the period. Find the period of y equals sine of the quantity x over 2 and use the language of transformations to describe how the graph relates to y equals sine of x. So how does the graph of y equals sine quantity x over 2 compare to y equals sine x? Let's take a look at what these two graphs look like. So here's a screenshot from our TI, and you'll notice that the blue curve is the sine function, and the red curve is sine of x over 2. And if we take a look here closely, what you're going to see is if I focus on the sine function first, okay, here's our origin, 0, 0. How long does it take the sine function to complete one cycle? What's its period? Well, its period, the blue curve goes up, down, and back up. When it gets to 0, that's one full cycle. That's the period of the sine function. And the period of the sine function is 2 pi. Okay, but if you notice the red curve actually takes much longer to complete one full cycle. Okay, if you trace along the red curve here, up, down, and back up, it doesn't complete one full cycle until the value is out here. And it's actually, I don't have any values on this axis, but this value is actually 4 pi. So twice as long. So if you notice, when we divide x by 2, or essentially what we're saying is multiply x by 1/2, the period is actually twice as long. So in general, when x has a coefficient of less than 1, it takes the function much longer to complete one full cycle. So it lengthens its period, and we call that a horizontal stretch. So think of it as taking both ends of that curve and just pulling it and stretching it out. And so here's a summary of that in words. But right here we have the calculation. Okay, remember our formula for period is 2 pi over the absolute value of b. Well, in this case, for this function, b is 1/2. So we get 2 pi over 1/2, which doubles 2 pi. And so again, we get that period of 4 pi. So let's talk about the frequency of a sinusoid. And frequency is very similar to period. You know, remember, the period of a function, sinusoid function, is how long does it take for the wave to complete one full cycle, or that function, the wave of the function, to complete one full cycle. Well, the frequency is the number of complete cycles the wave completes in what we call a unit interval. And a unit interval, if you think about think about the unit circle. How long does it take? How many degrees does it take to travel all the way around the unit circle? Well, the answer to that is 360 degrees. In radians, that's 2 pi. So what we're looking at when we talk about the frequency of a sinusoid is we're trying to figure out how many cycles of the wave does the function make in 360 degrees or 2 pi radians. And so the way that we calculate it is this formula here, which is basically the reciprocal of the period formula. Okay, so instead of 2 pi over the absolute value of b, we have the absolute value of b over 2 pi. So those two are related to each other. Alright, so combining a phase shift with a period change. We want to construct means write, a sinusoid with period pi over 3 and amplitude 4 that goes through the point 2, 0. So go ahead and pause the video and see what you can come up with. So we want to construct a sinusoid with period pi over 3 and amplitude 4 that goes through the point 2, 0. Define the coefficient of x. Set 2 pi over the absolute value of b equal to pi over 3 because that's the formula. Here's the formula for the period. And we are told that the period is pi over 3, so those two are equal to each other. And we have to solve for b. So when we solve for b, we get two values because of the absolute value. So we have a plus and minus 6. So we'll choose b equals 6. Most of the time we're going to choose the positive value. For the amplitude, set the absolute value of a equal to 4. And again, we'll just go ahead and choose the absolute value, positive 4. And the graph contains the point 2, 0. So think about what this does. This shifts the function 2 units to the right, graphically. Now when we shift graphically 2 units to the right, remember, that gives us a subtraction of 2 on x. So if we take our parent function, y equals sine x, and we insert the information that we have our amplitude of 4 here, we have our b value of 6 here. Now notice what we have to do here. We have to get our translation of our function 2 units to the right on x in parentheses, and then we have to multiply by 6. We have to distribute the 6. So it would not be appropriate to write this 6x minus 2. We have to write it 6 times the quantity x minus 2. So another example, we want to find the frequency of the function f of x equals negative 1/3 cosine 5x and interpret its meaning graphically. And we're going to take a look at the graph in the window, negative 2 pi over 5 to 2 pi over 5, and negative 1/3 to 1/3. So we know frequency to be the formula, absolute value of b over 2 pi. So if we apply that to this equation, our frequency is 5 over 2 pi. The reciprocal of that is the period, which is 2 pi over 5, which, remember, that tells us that this function completes one cycle in the interval 0 to 2 pi over 5. So starting here and ending here, this value right here is 2 pi over 5. Okay. Now you'll notice that this is the reflection of the cosine across the x-axis. And the reason is because the negative 1/3. The negative 1/3 cosine 5x means that not only is the amplitude 1/3 here, but this is also, because this is negative value, this is reflected. Normally the cosine function would start here and come down and then up and finish like this if we had positive 1/3 cosine 5x. But since we don't have that, this is what the graph looks like. It's the reflection. So when we have a negative coefficient on cosine, it actually is going to start down here on the negative y-axis. It's the reflection of that. Okay, so to summarize this a little bit, the graphs of y equals a sine b times the quantity x minus h, all that plus k, and the cosine of the same thing, where a not equal to 0 and b cannot equal 0, have the following characteristics. We talked about an amplitude, where amplitude is the absolute value of a. We talked about the period, where the formula for figuring out the period is 2 pi over the absolute value of b. And we talked about the frequency is the absolute value of b over 2 pi. Frequency and period are reciprocals of one another. When compared to the graphs of y equals a sine bx and y equals a cosine bx respectively, they also have the following characteristics: a phase shift of h and a vertical translation of k.